Many of us grew up with a specific linear image of science, usually a 6-step checklist on a classroom poster: observation, question, hypothesis, experiment, analysis, and conclusion. This creates the image of a solitary genius working in a sterile lab to discover absolute, unchanging truths. When we are taught that science is a list of fixed answers, we struggle when the consensus changes. We see a revised health guideline or an updated climate model and assume the process is failing us. But the method was never meant to be a static assembly line. In practice, it is a messy, creative, and highly skeptical toolkit used to interrogate reality one variable at a time. If we view science as a one-time proof rather than a process of continuous revision, we lose the ability to judge the information we consume. We either accept every headline without scrutiny, or we discard entire fields of study the moment a single finding is updated. Scientific inquiry does not begin by simply piling up facts. It starts with specific logical frameworks used to turn an observation into a testable hypothesis. Deductive reasoning is the top-down approach. You take a general rule and apply it to a specific case. The logic funnels down to a conclusion. Inductive reasoning builds upwards. You collect specific observations to propose a general rule. Abductive reasoning handles the gaps. This is how Sherlock Holmes operates, taking an incomplete set of clues to find the most likely explanation, like attributing a messy room to the dog rather than a highly improbable break-in. These aren't rigid categories. Scientists constantly shift between these logical gears to ensure their initial guess is actually worth testing. Once a hypothesis is ready, it enters the experiment, an arena designed to isolate one factor while ignoring the noise. Consider a simple test to see if fertilizer helps a plant grow taller. To define your variables, the independent variable is the single factor you deliberately change. The dependent variable is the outcome you measure based on that change. Finally, controlled variables are the background rules kept identical, ensuring nothing else skews the results. If you fail to isolate these factors, your data is useless. You won't know if the plant grew because of the fertilizer or because it accidentally received an extra cup of water. Even a perfect experiment doesn't offer absolute proof. Philosopher Karl Popper argued the true goal of science is not to prove an idea right, but to see if it can be proven wrong. This is falsifiability. A scientific claim must take a risk. It must offer a clear, conceivable test that could potentially refute it. This distinguishes science from pseudoscience. A horoscope is interpreted so broadly that it can be adapted to fit any outcome, meaning it never risks being proven wrong. Albert Einstein provided the classic example of falsifiability. He predicted that the sun's gravity would bend the light of distant stars by a very specific, measurable amount. Testing this required a solar eclipse and massive telescopes. If the light didn't bend exactly as Einstein calculated, his entire theory would have been discarded on the spot. Einstein's theory survived that test, but its strength doesn't come from how much we believe it to be true. It comes from how many rigorous attempts to prove it wrong it has successfully withstood. Science remains our most reliable tool for truth, specifically because it is never finished. By treating every conclusion as provisional, the method forces itself to incorporate new evidence as soon as it appears. Most of us use these gears every day. When a car engine fails to start, you don't just guess. You isolate the battery, test the connection, and rule out the starter, applying the same logic a researcher uses to map a genome. Using this toolkit shifts your focus from what is being claimed to how it was tested. It trains you to look past the top-line numbers and the headlines, asking, how do we know this, and what evidence would prove me wrong?